Good afternoon, YouTubers. I was watching this video and I found it quite interesting and how can we do sort of like a DC to DC, but increasing the voltage from a given node value to a higher value. And that was kind of interesting to me based on what this guy from organic chemistry tutor is showing something about electronics. So anybody can have fun with electronics. That's basically what I'm saying. And the funny thing is, it's very simple. And basically, a battery, when this is open, like shown here, it will go through and it will charge the capacitor. No problem there. The issue is when this close, the preferred path is going down, and that's when the inductor start to get a lot of energy. Now, the issue is when this part here open, sort of like a switch. When this open, the inductor become basically like another battery that is in series with this one. So these two batteries will then pass through the diode and will start to put that energy into the capacitor. So the capacitor will have a higher voltage than shown previously here. So that action will happen as you open and close this. So basically what we need is a MOSFET with a given amount of pulses per second to get the job done. And it's kind of neat. So you want to, I don't want to talk about the theory behind all this. I just want to build it and find out how well I can do that using Proteus. So with that in mind, let's move to Proteus so that we're gonna make our boost converter. And basically, the idea behind all this is an inverter. Eventually, I'm working on several videos about inverters, and one of the problems that I'm having with when I use 12 volts to 120 is that somehow it is better to control the input voltage to the transformer, and so you can control that. If you have a higher voltage, then when you put a load into that inverter, you will be able to maintain the 120, 125 volts AC even with the load. Just because if you have something like this that can change the voltage from 12 to whatever value you need here. So here you will have like a transformer and everything else. Well, actually you have all the circuitry with the MOSFET to allow for the changing of this voltage that is DC into sort of like an AC and so forth. So that's another story. I don't want to bog you down. The issue here, the important issue is that we want to make a boost converter, and let's start to work. So let's bring a battery here very quickly. This will do, no problem. Let's bring an inductor. Let's use air fill. Let's bring as well a MOSFET. A MOSFET. About IRFC. 44. Let's see, which one should I pick? Like this better. All right, 41 amps. Yeah, let's use that one. 44N. Okay. Now let's bring a diode. How about 1N 4148? Let's say okay. How about a capacitor? And a generic non-electric. Let's say that. How about resistor? Uh-huh. A resistor. That sounds okay. And let me start to put this together so that everybody knows, because basically what I'm looking at is something as shown previously on the YouTube page that I was watching. So let's start with the battery. Put the battery somewhere here. Now, let's add the here we go. Let's make this kind of big so that there's space for everything. Put it somewhere there. Actually, that would be there. Perfect. And now let's put this will be kind of an AC because it will oscillate. Let's put that there. See how much current going through that guy. So, oops. That will do. And now let's go back here and let's put the MOSFET somewhere here. Let's put the MOSFET right here in the middle. Actually, I can do like this. I want to see how much current go through the MOSFET as well. So, let's bring another of this guy. It's going to be an ACM meter. And it looks a little bit weird, but I'm going to leave it like that. And so let me drop this so I have an idea what I'm doing. Let's see. Let's add, keep adding here a cap. Will be actually, well, put the cap here somewhere. And let's turn that around. And let's add my diode somewhere here. And let's bring this to here. And let's bring this to here. And let's bring that one far enough to here. And things are getting pretty much the way I want it. And this could go here. And now I need my load. So that will be my resistor somewhere here. Let's turn that around. Let's turn that around. Good. And let's bring a DC meter so that we got this pretty much the way we want it. This will go here. And this will go here. Good. And this will go here. Good. So we know how much currents go through that resistor, and now we need a voltmeter. How about this is going to be a DC to compare how much voltage increase we have. Now everything looks good. Let's change some numbers here. Nanofarad. Let's put 100. Say 100 microfarad. That will do. The resistor is huge here. Let's drop that to, I don't know, 5. ohms, so that would pull a lot of current through, and 1 millihenry. 1 millihenry. Let's put I don't know. If here, be very careful. If you put a small value, the impedance when this close will be huge. I mean, will be very small. So this battery will drain right through with a very huge amount of current. So this value cannot be too small, this one here. So I don't know, maybe 100 microhenry. I don't know. We need to check the efficiency of this based on what he was talking about. And I think my circuit start to get in shape. I only need a reference for my ground. My ground will be, I don't know, put it somewhere here. Otherwise, I will have problem with Proteus. Almost done. I got a 9-volt battery. Since I'm planning to use 12-volt, actually, let's change this to 12. Okay, it's an ACM to measure the current going through the inductor, and then I have another here to be sure what much current is going through this guy, which is the MOSFET, and then got the capacitor for storing the energy, and I have here the DC amp meter to check how much current is going through this resistor, and at the same time measuring the voltage. So I can definitely calculate the efficiency of this system based on the amount of current that is kind of consumed through here, multiplied by that 12 volt, give you an efficiency. Give the number that is being consumed, divide the watts being consumed, divided by these numbers here, current time voltage, and this is the one that is being produced. So we want that to be, when you buy some of these suckers, boost converter, they claim that to be above 90%, so I'm not sure about that. Let's see. Anything else that I need to think about it? Oh yes, definitely. If I don't put here, the pulse is not gonna get anywhere. So let's see, it's gonna be a pulse, and let me put that somewhere here, and let's from here up to here. So I got the pulse, and now let's check the parameters. It's gonna be a pulse. Now that pulse, micro. Wow, I don't know about that. 1 micro might work. The pulse width 50%. Here's the nice things about it. I mean, you can vary it. I mean, if I use an Arduino that will do the pulse width, I can definitely see how the voltage will change here according to that pulse keeping the same frequency all the time. Let's start with 20K here. Let's start with 20K and let's see the pulse width. Let's put a small one, 20%. See what happens. Very little pulse. I don't know. Should I stay with the 1 micro? I would say so. How about the pulse voltage? If I don't put the right voltage for the MOSFET, it will not pass current through. So I gotta have at least 12 volts. So look good now. Let's say okay. Let's see if this blew up or it runs. I don't know. So it is running. I can see about 3 amps going through the inductor, and only about 2 amps going through the MOSFET, and about 3 amp going through the resistor of 5 ohms, and an increase of 2 volts. And so you might say, well, something is wrong. It should be higher voltage. Well, depend on the pulse that you're putting onto this guy, the width. And that's the kind of nice things to do this. If this were an Arduino, I would be able to change this on a fly, and that would be great. So expect me to do that boost converter with an Arduino later on. But at this time, I'm only testing concept here. So going back here, that's very little, 20%. How about 50%? So now I should see something getting better. Oh yes, it's twice the voltage. So here it's 12 volts. Right now it's about 22 volts, and I'm pulling about 5 amps, and about 9 amps are going through this guy here. Uh, you know, when I was doing this calculation, I put this out of the blue. Maybe this should be increased. I need to check the efficiency of where it is right now with this number, and so let's hold for let's stop here for a second and do some calculation. Like for example, what's the efficiency right now? And but out of the blue, very quickly I can see that this guy is having fun because very little current, about 7, and it can handle 41 amps. So I see it, and so let's pause here and let's grab those numbers and do an Excel quick calculation to find out what's the efficiency right now. So hold for 1 second here. So let's put some number here and let's find out. So let's say, for example, my input voltage is about 12 volts, and my input current is about 993 amps. So that means that the amount of input watts is about this guy time this guy, about 119 watts. And how about the output? The output size, the output voltage is about 22.7, and the output current that I'm pulling right now because of my load of 5 ohms, output here's current. Output current is about 455. That means that the watt that I'm consuming right now is about 103, and this is what? This is output watts. So what's the efficiency? The efficiency in percentage is about, we can do a quick calculation here. So that would be this number divided by this number, about 87%. Let's multiply that by 100, so we get this times 100. That's 87%. Low. Let's see. What's the main guy here who's discussing this trouble? Is the inductor. This table was done when the inductor was about 100. Let's see what happened here. The inductor was about 100 micros, or 100 microhenry. So what I need to do is, 22.7 increase, that's a 50%. That will do for me, for my inverter that I'm planning to work on. I can increase that voltage, but we want to compare oranges with oranges. So leave everything the way it is. Like, for example, if I double check here, stop this. If I double check this guy where he is right now, here, it's about 20K. and a 50%. If I increase the percentage of it, definitely the voltage will go up. Maybe the efficiency might go even worse than what it is right now. So, but the issue is this. I know that this is the guy that would determine how efficiently you are doing your conversion. So right now it's a 1,000, it's a 100 microhenry. So let's get that guy and let's step it up a little bit higher. Let's say 1,000. Now we had 1,000. And let's run the same way that we did. So let's run it. And so let's see whether the efficiency increases or not. So right now everything is the same. I got about 8. Yeah, I don't know. It's still cranking numbers there. 9, 9, and 968, 975. So let's see whether things got better or worse. So basically it's the same table that I have here. Copy, put it someplace else like here. But now change this guy. Now I'm using 1,000 microhenry. Let's figure out if that's true. Yeah, 1,000 microhenry. And now let's do the changes. So input current 990. I drop a little bit. 990, 990, and the this 455 and the output voltage kind of increased a little bit more. It's oscillating between 22 and 24, so I would not count too much on it. So, and the current 455, so it stayed the same. So the inductor from changing from 100 to 1,000 microhenry, it did not improve the efficiency, still on 86%, 87. What's next? Next will be changing the frequency of this guy. Using 20, about stop for here for a second, and let's see how well it behaves if I change this to 50K. Now let's run it. Let's see, I can increase the voltage here. It also increase the current. We'll see now. Yeah, definitely it improved a lot. 50K. Oh yes, oh this is a lot better. The current stayed pretty much the same here. Hitting the 10 there. It's almost getting there, getting stabilized. But definitely I can see an improvement in the output voltage and the current. So let's check the efficiency here. That's a 50K. Maybe I can get to 100 and it would be even better. So let's figure it out and let's stop this video. I don't want this video to be more longer than what it is right now. So let's copy this. And now, so one thing that I will do is add another column here, insert, just for me to understand what parameters we are using, is that the frequency here was about, this was 20K, 20K, I would not use that number for anything, and also that the frequency here was as well 20K. Now, but the frequency here, I increased it to let's say 50K. And let's see the numbers. Here the number looks a lot better. So the current input is 11.7. That increased the watt usage to 140, but the output, let's see, where's the output? The output is 5 amps. The output current was is about 5 amps, and the voltage is about 20, 25, 25. So increase it from basically from 86 to 89. Now it's getting to almost to the 90. The only thing left is, I don't know, should I do one more? Is to increase the oscillation, the pulses here. Let's get this bigger. Is to increase this guy. Let me stop to 100K. And let's figure it out whether it will do any good. It's ramping up. It's not yet 1 second on my computer, so it's taking for a while. Oh, definitely the voltage is getting almost to 30, and the amps about 6 amp here, and the current still going up here. I'm about 0.1 of a second, and the computer is heavily loaded. Well, it's dropped to, it was, I saw 41 here, but now it's going back to 64. So I'm a 1/10 of a second, and the voltage still, the current is still going up, and maybe did I hit the 90% now? About 100 K, the pulses here, and they are also about 50%. So let it run a little bit until I think that they are stabilized already in about 2/10 of a second, and I guess that we can pause here to get the numbers right. All right, so last calculation, and we are done. We call for today. All right, so let's put this somewhere here, big enough that I can see the numbers. And so let's copy the whole thing, and let's put it here again. And the only difference is that this is 100K. And now the input voltage was still 12, but the input current increased to 15.5. So I got 15.5, 186 watt, and the output voltage about 29.5, and the current about 590. There we go. About 90, 94. That did pretty good. That did pretty good. So I guess that yes, indeed. Let me get this. So that's, now you have it. That's as simple as you can get. A boost converter, I was able to change from 12 volt down to 30 volts, and I definitely think that I can increase to a higher value, obviously, and that will depend on the frequency and the parameters that you're using. Kind of wondering, if this voltage can increase to a little bit higher value, and the question is, I believe so. Let's see. Let's stop here for 1 second. Remember that all these studies are done at 50% on the pulses. If I increase, let's say 70%, that would be interesting, because that's a lot. Let's see, what would that do? Now, at 70% on the pulse, everybody was at 50. Remember that. All this study was done at 50, but now that's increasing to 70%. Now I can see a lot of current going through the MOSFET now, close to, and I see a lot of current going through the inductor. So, wow, the voltage have increased to almost 50 volt, 50 times 10. That's 500 watts right here. The output with the input in the neighborhood of that number times the battery voltage, which is 12. Yeah, it looks very high efficiency to me, just because I increased the. Wow, I think that this looks good. In fact, looks so good that I want to finish with this. So basically, I changed the pulse to 70% duration, and but definitely there's a problem here. I exceeded. I think that the design of this guy. In order for this to work, definitely this will have to. I don't know. You have to have two of this guy, because right now in parallel, because right now it's pushing 51 amps, 52 amps, and I'm 2/10 of a second. I think that is already stabilized. So let's see the efficiency where we are, whether it dropped or not. So let's pause this. So I got the numbers, and so I'm missing one thing on this table, but I fixed it. Copy. I want to be sure that I copy that for my reference, and that will be like, for example, yes, the frequency was that, but the width the width of that frequency was about 70%, meaning that the others uh, 70%, that the other were at 50. I want to be sure that I remember that, and that this guy was also at a higher 100K. Any doubt, you can always check, because of my last numbers here. So in fact, let's double check where we are. Let's leave it that. I check it out later. So it's 100K. Now let's change numbers here. So input voltage is still 12, but the current was now 60.2. Wow. Input current 60.2. And input was 722. How about the output? The output increased to 50.4, and the output current 10.1, and the output was 509. So by increasing the duration of the pulses to 10, the efficiency dropped to 70%. That's not good. But, well, I guess now you have it, guys. You can keep messing with this until, but I think that's more than enough. Basically, a boost converter, as simple as I can get. You can do some checking on the. You can still increase this one to find out whether you can improve the efficiency of these guys. But so far, looks good to me. Very promising that I can take a battery of 12 volt and take it to as high as 50 volt, and I'm still, at 70% on the width of the pulses. So there's room for increasing that voltage to a higher value, but at a cost of the efficiency. Again, thank you for watching. Have a great day. Bye.